First of all, I would like to, well, tell a few words about the general background and the main interest maybe in the higher spin theories these days is because of the ADS-CFT correspondence. The original idea was put forward by Sandberg and Witten long ago in 2001, who speculated on a possible relation between massless theories at the boundary and string theory and other bulk theories. But more concrete conjecture in relation with higher spin theories was actually made by Klebanov and Polyakov next year, who conjectured duality between higher spin theories in ADS4 and vectorial conformal models in 3 dimensions. So after that, there was a lot of work on this, especially after the paper by Jomby and Ian appeared in 2009, where this conjecture was explicitly checked for some particular cases. And now this topic is quite active and very, very interesting, so I'm not just able to give you a full even list of names who is taking, well, working on this subject. Here are just some important works. And also the original conjecture has been generalized and extended to other cases by Gabardil and Gopakumar, in particular to ADS3 CFT2 correspondence, and that is related to the yesterday's talk of Rajesh. And also some other cases were considered. So I think that analysis of higher spin holography is very interesting because, among other things, it may even help to uncover the origin of holography. And I think this is what goes on these days. Somehow we have a chance to understand better the mechanism behind it. Maybe I will make some comments towards the end of my talk on this general issue as well. So to begin with, let me remind you some generalities about the formulation of higher spin theories, which is most useful in the context of the full nonlinear theory. So the standard machinery is what is sometimes called unfolded dynamics. This is just a first-order covariant formulation of dynamical field equations, which means that fields are differential forms of various ranks, and the exterior derivative of every field is expressed in terms of wedge products of the same set of fields. So I will never use this wedge product after this slide, so all products are wedge products from now on. Well, naively it looks like that this formulation is very special. In fact, it is not. One can proceed this way for basically any system of partial differential equations by introducing more additional fields if necessary. Well, whatever it is, if this system is consistent, then actually because d squares to 0, then there should be some compatibility condition imposed on the function g. It should be obeyed for any fields w. So this is identity, generalized Jacobi identity, that should be satisfied by the function g. It's in no way equation on w. Once it is true, then actually there are gauge symmetries which follow from as a consequence of this condition. One can check that this system is gauge invariant. So such a formulation has a lot of very interesting properties. I have no time to focus on most of them. I would like to emphasize just one, which is most relevant to the holography issue. Once we manage to reformulate one system or another in this form, then actually it follows that somehow the dependence on x is somewhere deep inside, so it's even not visible. It doesn't matter how many coordinates serve for this differential derivative d. And this allows us to play with number of dimensions just by adding extra dimensions, like, for example, z, that refers to the Poincare coordinates in the ADS-CFT correspondence context, or remove. I mean, changing these coordinates does not affect the content of this system, even though the concrete differential equations in one or another spacetime may look very, very differently. And this happens because the problem is, the initial data problem is fixed in terms of values of fields at a given point once we know how to express all derivatives. So it's enough to fix fields at a given point, in fact, zero forms by Poincare lemma, to reconstruct everything, at least locally. Of course, this is a local statement, and the non-trivial topology issue is not touched here. But up to this subtleties, actually, everything is fixed by values at a given point, and it doesn't matter whether we take a given point in one space or another. It's still a given point. So that suggests that maybe there is a chance to characterize equivalence classes with respect to holographic duality just by saying that these are theories that have the same function g, maybe in different space-time dimensions. And that is going to really happen. I will discuss this a little bit in more detail, and we'll give some examples in the rest of my talk. All right, so let me give a simple example how it works. And actually, this example is very important in the context of ADS4 CFT3. Well, first, this is how the massless field equations in 2+1 dimensions can be written in this unfolded form, where all derivatives are expressed in terms of the same set of fields. So to this end, one introduces a field that either can be interpreted as an infinite tower of component fields carrying more and more spinor indices, or as a function of auxiliary variable y, which is a commuting spinor variable, carrying spinor indices alpha, beta, taking two values in 2+1 spacetime. So one can see that the meaning of this system is actually very simple. First, one can read it like that all terms containing two y's or more are expressed in terms of higher derivatives of the other fields. And the other fields are just a scalar, which is y-independent part, or a spinor, which is linear in y. So there are two dynamical fields, spinor and scalar. And one can check that they obey Klein-Gordon and Dirac equation as a consequence of this. So this is an equivalent way to formulate usual field equations, which are free field equations, in 2+1 dimensional space. Well, this example is very simple, useful, and interesting. So the next question, whether we can proceed similarly for somewhat more, maybe more general systems, and how can we do this? By the way, once the system is formulated this way, it is manifestly conformal invariant simply because conformal group acts on the functions of y as on the Fock module of the appropriate oscillator realization of the conformal algebra, which is SP4 in this case. Well, the question is whether or not we can consider other SP4 invariant equations. And the simplest case is just to double the number of spinor variables just by introduce u and y instead of single y. And this is what we call rank 2. Rank refers to the number of spinor variables. In terms of representation theory, this means that we take a tensor product of the original modulus for massless fields. And this equation actually was shown long ago to describe conserved currents at the boundary. Independently of how this what they are built from, just those currents that obey these equations are just conserved and conformal. To get the standard relation for conserved currents in terms of free fields, one can use this formula. So the very elementary fact, just chain rules, nothing else, is that once C obey these rank 1 equations, then J obey this rank 2 equation. And one can see that this formula just gives rise to all conserved currents of massless fields which are conformal and which contain all higher spin currents as well. Again, one can analyze what are primary fields, namely those that are not expressed in terms of derivatives of the others. Here is the least. And of course, the appropriate conformal weights are as they should be for conserved currents. So one just gets the whole list of primaries for conformal currents from this equation. So this is an example that has been studied in great details, and actually this is the example that underlies CFT3 ADS4, because this equation that describes conformal currents, it remains to add Poincare coordinate actually to promote this equation to massless equations in 4 dimensions. This is a very simple exercise. Well, there is a little one should take care that this is ADS, but apart from that, this is simple in Poincare coordinates. Good. So the questions that I'm going to address in this talk is how can we generalize this scheme? And there are, in principle, a priori 2 types of generalizations. And actually, one is known for a long time. Again, one thing that one can do, one can let the spinor indices, which here are called by capital letters because they may take other different number of values, let them to take more values, which is called by letter m. But normally, to make it possible to interpret them as spinor indices, this m is chosen usually as the power of 2. That was actually observed by Fronsdal in the 80s, that such an extension is very useful to describe massless fields in 4 dimensions. And the same observation was made later on independently by Bandelslu, Kirsti, and Sorokin. And actually, this form of equations was then proposed in 2001. OK, so here we have matrix coordinates, which are symmetric matrices, m by m. Y's take just our spinor variables, but now these are spinors of higher dimensional space. And differentials are called psi, just to simplify formula in the rest of my talk. What I would like to emphasize is that a relation of this letter m to the actual dimension of space-time related to this scheme is quite non-trivial. And the first dimensions that appear are precisely 3, 4, 6, and 10. And this is related to the existence of twistor formulation, actually. So it's not just directly D. It's a little bit more subtle. But this is about higher dimensional physics anyway. Well, one can derive equations of motion for fields. So fields are, again, it's just y-independent part and y-linear, because all components containing 2 y's or more, they are expressed in terms of derivatives, x derivatives of the others. So there are 2 fields. And in 4 dimensions, they just describe all massless fields of all spins in a single scalar for bosons and a spinor for fermions. And these are generalized Klein-Gordon-like and Dirac-like equations that are obeyed by these fields. Again, this stuff is known for a long time. And this is not particularly new. Nothing new is there. So what else can we do? An other option is just to play with a number of spinor variables y. We can consider let more spinor types, species of spinor variables be around, generalizing our equations to equation like this, where there is a summation over different y's. This is what we call rank R system. So remember that current system was a rank 2 system for the original massless field. So now we wonder what would happen for higher ranks. Well, and the main result that I want to announce is basically the structure of the corresponding fields and field equations for these higher ranks fields, one of the main results. But before doing that, I would like to emphasize that here there is a very interesting interplay between multi-particle states in lower dimensions and single particle states in higher dimensions. Well, number one is taking several y variables is essentially equivalent to taking a tensor product of the original space, which is the same as taking space of multi-particle states in the original free theory. So we are talking actually about multi-particle states in the original theory if we go to higher ranks. That's number one. Number two, what we can do, we can just denote these variables by a new variable with a twiddled index a running from 1 to Rm. And then we see that actually this system can be embedded into a rank 1 system in a much higher dimensions where m is multiple of r to the original value of m. So in that case, well, this rank R system can be obtained through the projection to the diagonal coordinates. So we can actually consider a reduction of the rank 1 system in higher dimensions to the rank R system in lower dimensions by identifying the coordinates in the original m space with characterized by m values taken by spinor indices, which are embedded diagonally. So x11 is equals to x22 and so on and so forth, and all of them are equal to the original coordinates. So that's no. OK. All right, that makes things actually simpler. All right, so that is the equivalence between rank 1 and rank R in different dimensions. So as I said, what the problem was to analyze all the field equations and all fields and field equations. This is the final result. Actually, to analyze fields is a very simple problem. You can immediately see that they are characterized by various traceless rank traceless tensors with respect to the OR group that rotates indices I and J. While a little bit more complicated problem was to analyze field equations, and this is one of the results that I want to present. And here are the equations, which are some differential equations with respect to x coordinates of particular degree related to rank and related to the type of the Young diagram that is associated to the field. And the rule is that the Young diagram properties of the left-hand side of field equations somehow are related to the Young diagram properties of the fields by the rule that the total heights of the first two columns should be exactly r plus 1, where r is the rank. OK, so that's the next issue is how to derive currents. To put it very quickly, we can actually analyze conserved currents. Conserved currents means that we have to find whether or not there are closed forms that are built in terms of the corresponding solutions of the corresponding equations. And the answer is that, yes, there are closed forms of this degree, which is a huge degree if we think in terms of the original space. So they cannot even be integrated, these forms, in the original space, but they can be integrated in a higher space. And actually, one can consider some multi-particle currents that give rise to conserved objects. And these objects, they are not correspond to local objects in the original space-time, but they can be either integrated in the larger space, or they can be interpreted as a non-polynomial, non-local object in the original space. Basically, these currents, they give rise to conserved charges, and these are just conserved charges that give rise probably to the multi-particle symmetry algebra that was conjectured to underlie the higher spin algebra and is pretty much related to the constructions that was considered in the yesterday's nice talk by Rajesh. So I think this is how the symmetries or symmetries of that type are realized in terms of these fields. Well, OK, so I'm forced to skip the rest of this part because just let me announce that the point is that we also computed all higher sigma minus cohomology, which in physical terms means that we found the field equations and fields that correspond to higher differential forms described in the same space. So we have the same number of y's, but we can consider not necessarily zero forms, but higher forms, gauge fields. And we found the full list of cohomology, which means the full list of fields, gauge symmetries, and field equations. To have gauge fields around is important for the nonlinear theory. Unfortunately, I cannot say much about the technology, which is actually beautiful, because a problem like that is not quite trivial to find all this cohomology. And it turned out to be possible to do it in a nice way. Unfortunately, I'm running out of time. So let me switch to the other topic. That was announcement number 1. Here will be announcement number 2. I would like to make some comments on invariant functionals in the Harshman theory. So normally, what we know are field equations. And it's generally believed that, well, it's difficult to construct action, and, well, some people say it's impossible, and so on and so forth. So let me discuss this issue. Well, number 1, if there are some unfolded equations, then there is a very general technology that allows one to reconstruct gauge invariant functionals that can be constructed on the solutions of these equations. Well, the point is simply that one can rewrite this equation in this form, where q is just operator g d dy. And then this q squares to 0. This is just the compatibility condition. And the final answer is that invariant functionals are precisely characterized by q cohomology of this operator. So if we find some q-closed operator which are not q-exact, we get some invariant functional s as an integral of appropriate Lagrangian. So far, well, this works for off-shell and on-shell. So here is the system of nonlinear Harshman equations as it is usually used these days. So it is formulated in terms of two kinds of fields. W is a set of differential forms, both in axis and in the auxiliary spinor variables. And there is a zero form B. So there are, in these terms, just two equations. That curvature is expressed in terms of B, let's say. Well, there are some subtleties about the Klein operator that I should skip, and the star product is very special. So, but this is the form for some special value of f, choice of f. So this is what gives rise to the four-dimensional equations for all higher spins and lower spins as well. All right, so this is the on-shell system, and the question is whether or not there is a chance to construct the action. Well, the comment I would like to make is, first of all, that we probably don't need action at all, because what we probably need is the on-shell action. And this is precisely what can be captured captured by this problem setting. So what we should do, we should find Q homology for this system. We should find invariant functionals for this system, and that is enough. So that's probably would solve the problem for constructing the generating functional, in particular in ADS-CFT correspondence. Well, let me give you just some idea how one can do this. I will not give the all detail, but the main idea is the following. Well, first let me remind you a little bit about the meaning of the fields that appear in these formulations. There are two sorts of fields. The zero-form field B, it's actually related to zero forms which are responsible for gauge invariant objects like scalar field, like Faraday tensor, like linearized Wild tensor, and all higher spin counterparts. And also there is a gauge field omega, which is a gauge field for higher spin fields. From the bulk perspectives, these fields are related. So the C is just appropriate derivative of omega, which is gauge invariant under linearized gauge transformations and covariant under non-linearized. Well, the point is that if we want to analyze the functional that would give rise to correlators in the ADS-CFT correspondence scheme, then this functional should have this form at the linearized level. If it's omega times C, then it's basically, it's pretty much like the product of source, which is omega, to the current, which is C here, because C actually carries precisely those values, those conformal weights, as currents is supposed to have. So this is very much looks like similar to the generating function for the correlators of currents. And indeed, just plugging in a half here, because this functional is symmetric, and this means that second derivative will bring a factor of 2. Omega is not, C is not independent, C is a function of omega, actually gives rise to the appropriate generating functions for two-point correlators in this language. So the problem is whether or not we can construct a functional that would complete this formula to all nonlinear orders. And the answer that I'm announcing, not showing all details, is that the answer is yes. There is a way how one can reconstruct this functional, basically, roughly speaking, very much like reconstructing all nonlinear corrections to field equations. And one of the most important ingredients of this construction is that actually one has to add more differential forms to the original construction. So basically, the main ingredient that one should extend the system to, roughly speaking, the same form. Just its F gets changed a little bit. But the fields are now not only one forms, but also three forms, and so on and so forth. And B is not just zero form, but also two forms, and in principle, higher even forms of even degree. So in these terms, one can construct a functional that will be shown explicitly in the paper soon. And let me just make a final comment before finishing, is that what is important in this language, what I probably forgot explicitly to mention, I should mention, is that when we consider this formalism, Q, if some functional is Q-closed, this means that this is declosed. So basically, our functionals constructed this way, they are closed functionals. And that's why we can play with integration contours in this language. And one interesting option is to deform contour in such a way, slightly different from what usually is done, but seems to be very appropriate, is to integrate over around the z equals 0, which is infinity in anti-de Sitter space, taking just a contour integral using the Cauchy theorem. And that seems to lead to very nice formula for the generating functional for all endpoint correlators that follow from this construction. Well, at least in the three-dimensional conformal theory where there are no anomalies, which means that there are no logarithmic behavior. Okay, so I'm coming to the last slide. So these are conclusions. Number one is that I announced that all these sp2 invariant fields, currents, and field equations were classified. And there is a relation between high-rank fields and multiparticle states. All this about the theory of multiparticle states in the end of the day. Well, there is a way to construct these invariant functionals for interacting Harshman theories. And finally, let me just mention that analysis of this issue actually resolves some puzzle in the theory. There was some freedom in adding nonlinear terms in equations. And from this analysis, it follows that actually only linear terms are compatible with conformal symmetry at the boundary. So nonlinear, they just break down conformal symmetry somehow, and they should not be allowed from the very beginning. So let me stop here.